Hey everyone, and welcome. In science, a lot of the time, we start with a super simple model to get a handle on things. But reality, it's always a little more complicated and honestly, a lot more interesting. So today, we're going to dive into one of the best examples of this, the story of ideal versus real gases. So let's kick things off with a kind of weird question. What if gas particles were just ghosts? Seriously, imagine they were just these tiny, tiny points that took up zero space and could pass right through each other without feeling any attraction or any repulsion. It sounds a little out there, I know, but this is the key idea behind our perfect starting model. Now, this whole ghost particle idea, it's not just some fun little thought experiment. It's actually the bedrock, the foundation for this super powerful tool scientists use called the ideal gas model. You can think of it as the perfect blueprint for how gases should behave in a perfectly simple world. So what is an ideal gas officially? Well, it's a hypothetical gas. And that word hypothetical is everything here. The thing is, it doesn't actually exist in the real world. We pretend its particles are just tiny dots with no volume, and crucially, they don't interact with each other at all. No attraction, no repulsion, they just bounce around completely independent. And because this gas is so perfectly simple, it gets to follow this incredibly clean, simple rulebook, the ideal gas law, PV equals nRT. It's this beautiful, elegant equation that connects a gas's pressure, volume, and temperature in this really clean, predictable way. I mean, for scientists, this is the dream for describing how a gas behaves. Okay, but for an equation that simple to actually work, we've got to agree on a few ground rules. We have to make some assumptions about our ideal world to keep everything neat and tidy. So what are the rules in this perfect little game? Well, rule number one, the molecules themselves have zero volume. They're just points floating in space. Rule two, they could not care less about each other. They're completely indifferent with no forces pulling them together or pushing them apart. And third, every single collision is perfect. Think of it like super bouncy billiard balls that never ever lose energy. In theory, it's a system that could just run forever. Look, this model is awesome. It's fantastic for getting your head around the basics and for doing calculations under pretty normal conditions. But what happens when we take this perfect blueprint out of the clean, theoretical lab and try to use it in the messy, complicated real world? Where does it start to fall apart? Yeah, because let's be honest, the real world is messy. The simple rules don't always apply, and our perfect model starts to show some pretty big cracks. And this is where you can see the cracks start to form. Our perfect model works like a charm when it's hot and the pressure is low. Why? Because the particles are super far apart and moving way too fast to notice each other. But the moment you start to cool things down or really squeeze them together under high pressure, the particles get crowded. And suddenly, all those little details we ignored, like their actual size and the fact they can attract each other, they start to matter a lot. And that, my friends, brings us to the star of the real world, the real gas. This is the gas that doesn't always play by the simple rules. This is the air we're breathing right now, the nitrogen, the oxygen. This is the stuff that actually makes our world work. So what's a real gas? Well, it's pretty much what it says on the tin. It's an actual gas. And it strays from that perfect ideal behavior for two really common sense reasons. Its particles actually do have a size, they take up space, and they absolutely exert forces on each other. All right, so let's put these side by side. These are the rules of reality. First off, molecules aren't just little dots. They have a real volume. They take up physical space. Second, they aren't indifferent. There are real forces of attraction and repulsion happening between them. And their collisions? Not always perfect. Energy can be lost. These are the real-world facts that explain why that simple PV equals nRT equation starts to give us the wrong answers, especially when things get crowded. So, if the simple rulebook doesn't work for real gases, what do? Just throw our hands up and give up? No way! Scientists did what they do best. They wrote an upgraded rulebook, a much more sophisticated equation that actually accounts for all this real-world messiness. And this is it, the van der Waals equation. Okay, I get it. It looks a little scary compared to good old PV equals nRT. But trust me, all it is our original ideal gas law with a couple of clever reality corrections built right in. And these corrections are actually pretty genius in their simplicity. The equation adds these two little letters, A and B. You can think of the A term as the attraction correction. It deals with the forces pulling molecules together. And the B term, that's the bulk correction.
It subtracts out the tiny bit of space the molecules themselves take up. It's basically the math finally admitting, okay, yeah, these things take up space and they actually stick to each other a bit.
All right, let's wrap this up with a quick side-by-side. In ideal gas, we pretend it has zero volume and no intermolecular forces, so it follows PV equals nRT perfectly. A real gas? Well, it has particles with a real finite volume and real